In this video, we're going to collect together a few more examples of groups. And again, my aim is to show you that actually you already know very many and very diverse examples of groups. So to begin with, let's talk about some additive groups. So additive means that the group operation is some kind of addition. To begin with, as we've already seen, Z is a group under addition. So Z is an additive group. Similarly, the real numbers are a group under addition. The complex numbers are a group under addition. The set of all m by n matrices with real entries or complex entries are all groups under addition. So the zero elements, let me say this again, the identity elements would be the appropriate zero objects in this case, because 0 is what behaves like an identity element for addition. So in Z or R or C, the identity element would be 0. In these groups of matrices, the identity element would be the 0 matrix. On the other hand, n is not a group under plus. So the reason that n is not a group under plus is, well, let's check the axioms. First of all, when you're checking something as a group, you actually have one kind of extra thing which people often forget about, which is the definition of a group is that you have a set and a binary operation on that set satisfying the three group axioms. So if somebody just gives you something, so it gives you a set and something they claim is a binary operation, then you need to check not only that the axioms hold, but also that the thing they claim is a binary operation really is a binary operation. Now in this case, plus is a binary operation on the natural numbers. So that's kind of step 0 in checking something as a group. Certainly when you add two natural numbers, the result is another natural number. So plus is a binary operation on n. If we try to check the other operations, well, according to my definition, the natural numbers contain 0. So that means there is an identity element for addition. But we do not have inverses. So the inverse axiom is false here. The identity, as we've said, is 0. But one instance of the inverses axiom would be that for any natural number, so particularly the natural number, let's say 5, there should exist another natural number such that when you add them together on either side, you get 0. But that's not true, so there is no element x in n such that x plus 5 and 5 plus x is equal to 0. There's nothing special about 5, obviously. You could pick any natural number except 0, and you'll find that there's no natural number such that when you add it, you get 0. So the identity axiom failed, and that's actually, the inverses axiom failed, and that's actually the only axiom which is false. Certainly, natural number addition is associative, so that one passes. Okay, let's move on to another example of something which is not a group, which is Z is not a group under the binary operation minus. So minus really is a binary operation on Z because when you subtract two integers, you get another integer. You should contrast that with the fact that minus is not an operation on a binary operation on the set of natural numbers, because when you subtract two natural numbers, you don't always get another natural number. So why is Z not a group under minus? Well, one simple reason is that it is not associative, and this is a good example of a non-associative operation. So let's look at why it's not associative. I'm not saying this is the only reason it fails to be a group, but it's going to be the reason we look at. So the reason is if you do 1 minus 2 minus 3, and if you do 1 minus 2 minus 3, well, what do you get? 1 minus 2 minus 3 is 1 minus minus 1, so that is 2. But here 1 minus 2 is minus 1, minus 3 is minus 4. Okay, and these two things are not equal. So it's not associative. You can't get rid of the brackets. Let's now look at some multiplicative groups. And again, multiplicative group is just an informal term meaning a group where the group operation looks something like a kind of multiplication. So as we discussed before, if you take the set of real numbers with the binary operation multiplication, well, that really is a binary operation because when you multiply any two real numbers, the result is again a real number. but that structure is not a group. And the reason we saw was that the identity must be the number 1, but then the inverses axiom fails because there is no multiplicative inverse for 0. Similarly, the set of all complex numbers together with multiplication is not a group for exactly the same reason. On the other hand, if we let R cross, so R times, however you like to call it, be the set of all non-zero real numbers, and if we let C cross be the set of all non-zero complex numbers, then I've not done a very good job of writing this here. Let's try and write this again. So R together with the binary operation, R cross together with the binary operation of multiplication, and C cross together with the binary operation of multiplication are both groups. So they're both associative because real or complex number multiplication is associative. They both have identities, namely the number 1. They both have inverses because whenever you have a non-zero real or complex number, then 1 over that real or complex number is again a non-zero real or complex number, and that is your multiplicative inverse. And they both have identity 1, and multiplication really is a binary operation on those sets. If you multiply together 2 non-zero complex numbers or 2 non-zero real numbers, the result is another non-zero real number or non-zero complex number. Okay, so for a non-example, if you take the set of all n by n real matrices, it does have a matrix multiplication operation on it. You can multiply together 2 n by n real matrices, and the result is another n by n real matrix. But that doesn't make it into a group. And the problem is similar to the problem we had with the set of real numbers together with the binary operation of multiplication, which is there is only one possible candidate for the identity, which is the identity matrix, and that does indeed serve as an identity element for multiplication, but there are lots of elements which make the inverses axiom false. So there are lots of non-invertible matrices, such as the zero matrix, but this time there are lots of other non-zero matrices which are not invertible. So the problem is slightly worse than the problem we had for the set of real numbers under multiplication. So instead, what we have to do is just form the set of all invertible real matrices, and that will be a group under matrix multiplication. There's a special name for that, so GLNR refers to the set of all invertible n by n real matrices. So there's a extra restriction there. GLNR means the set of n by n invertible matrices with real entries. It's a group under matrix multiplication for the following reason. So condition 0, if you multiply together 2 invertible matrices, so you multiply together AB, then that is invertible, and its inverse is b to the minus 1, a to the minus 1. So matrix multiplication is a binary operation on GLNR. There is an identity element because the identity matrix is an identity element for matrix multiplication. The inverses axiom is true because, by definition, if you're an element of GLNR, then you have an inverse. And finally, matrix multiplication is associative, as we saw when we defined matrix multiplication. So we've met all 3 group axioms, and matrix multiplication really is a binary operation on that set, so it really is a group. And of course, you don't have to just deal with real matrices. GLNC refers to the set of all invertible n by n complex matrices, and that, for the same reason as before, is a group under matrix multiplication. So those are some examples of groups where the group operation looks as some kind of multiplication. So finally, let's think about some groups of permutations. So we've seen previously the set Sn of all permutations of the set 1, 2, 3 up to n is a group under composition. So that symbol there means composition of functions. Equally, there is another group inside Sn, which we write as An, and we define that to be all the even permutations in Sn. Now that is also a group under composition. So let's see why that is true. So why is this true? So first of all, we need to know that composition really is a binary operation on AN. So if you have two even permutations, so let's say A and B are even permutations, then you know that when you compose two even permutations, the result is again even. That means that composition really is a binary operation on AN, because when you compose two elements of AN, two even permutations, you get another even permutation, that is another element of AN. So that's condition 0 for being a group. Sometimes if you read other group theory sources, you hear people refer to this property of the binary operation really actually being a binary operation as closure. So if people talk about closure under the group operation or closure under multiplication, that's what they're talking about. They're saying, is the binary operation really a binary operation? So that's condition 0. Condition 1 is we need to show there's an identity element. So part 1, the identity permutation is even. So we know this. So it belongs to AN, and of course it behaves as an identity element for composition of functions. So the identity axiom is true. Next, we need to show that the inverses axiom holds. So we must show that for every element of AN, there is an inverse under composition for that element in AN. Well, if you have a permutation A, you know its inverse is again a permutation. But what's more, the inverse of an even permutation is even. Again, we proved this when we learned about even and odd permutations. So the inverse exists as an element of Sn, but it's also even. So A inverse is in AN again. Okay, and A composed with A inverse is the identity element for AN, no matter which way round you do it. So we've shown for each element of AN there is an inverse under composition for that element, which is again in AN. So we have axiom 2, okay. And finally, axiom 3, well this then is just easy because composition, function composition is always associative. Okay, so AN together with the operation, with the binary operation of function composition satisfied all three axioms, and therefore it is a group. So one final example here, you can check if you like that this thing is a group under composition. And this time there really is something to check when you need to verify that the composition really is a binary operation. You have to check that if I compose any two out of those three permutations, I get another permutation belonging to this set. And there's really something to check there. It's not immediately obvious that when you compose two of those permutations, the result should be another one in that set. So you need to check that. And when you've checked this, you'll know that composition is a binary operation on that set. And then you can ask three questions. So is there an identity? Yes. Is it closed under taking inverses? So does every element have an inverse? Well, you need to check. And in fact, it's true. The identity is its own inverse. 1, 2, 3 is the inverse of 1, 3, 2. And 1, 3, 2 is the inverse of 1, 2, 3. And you need to check associativity. But again, the operation is composition of functions. And composition of functions is always associative. So this thing really is a group. So this is the end of this collection of examples, but it's not the end of the examples we're going to collect. There will be separate videos later on about two of the most important categories of examples of groups. Firstly, we'll look at groups of symmetries of shapes. So these things will be called dihedral groups, and that's the group of symmetries of a regular polygon in the plane. So those produce some really interesting examples of finite groups. We will also look at the groups which arise out of what's called modular arithmetic. So those things, looking at addition where you pretend that certain numbers are equal to 0, so when you look at what you might call clock arithmetic, those things form very interesting and important examples of groups, both under addition and actually under multiplication as well when you make the appropriate modifications. So we will also have a separate video of those later on.